Hi folks, we're going to do an example problem here that tries to bring in a lot of different concepts, and we're going to focus on a breakwater design here, okay? So we are going to design an emerged breakwater, as you can see here in this sort of a schematic, a 2D sort of a scenario. We're doing a run-of-the-mill rock-armored rubble-mound breakwater. We're going to assume we have slopes of 1 to 1.5, permeable emerged, meaning sticking up out of the water for these conditions that you see here. We're going to have design waves that have the offshore wave height and period that you see there, so 6 meters, very big waves. And we're going to consider two water levels, a low water level and a high water level, where the depth at the toe is going to be 4.6 meters for the low water level, and then it will be 2.2 meters above that for the high water level. Okay? So what are we going to focus on here? We're going to focus on a couple of different design objectives. Okay, the first one is we are going to say that we want minimal overtopping. Okay, so that's kind of a harsh constraint for a breakwater. It's a typical constraint for a coastal dike, and we'll talk about that later. But this is kind of a harsh constraint or a difficult constraint for a breakwater, and that will lead to some interesting results for our structure that we design. We're going to say we want no armor damage at all, so 0 to 5% damage. So remember, damage means displacement, so we don't want any movement of the armor. And we're going to require a wave height on the other side of the structure, so over here on the transmitted side, of less than 0.6 meters. And that may be because of navigational constraints within a harbor or something like that. Now, we're going to make some assumptions, and a lot of these assumptions are kind of driven by what we can do with the equations that we know how to use in this class, but they can be relaxed if you have more exotic design tools at your disposal. So the first one is we're just looking at perpendicular incidence of the wave, so everything that you can see in this sort of side view is what's going on. The waves are not coming in and out of the page. What else? We're not going to think about sort of complex design scenarios involving risk or joint probability. We have these 25-year waves here. We're saying we have some range of water levels. We're just going to throw those 25-year waves in both of the different extreme water levels and think about these as the extreme conditions we're designing for. Normally you might get a little more fancy and think about whether you want to use a 25-year return period for the armor and maybe a lower return period for something else depending on the risk of failure. But we're just going to use these as sort of our design conditions, okay? So nothing fancy, just looking at these design waves. They're in deep water, and then the water levels will change high and low. All right, some quick and dirty estimates. These are always very important because ultimately we want to be able to answer whether our answers make sense once we do more detailed calculations. So in order to do that, we have to have some idea of what we expect going into the calculations. The first one is to notice that the wave height offshore is 6.3 meters. And if you look at the depth near shore, it's varying between 4.6 and 6.8 meters, okay? Which means that the offshore wave height over here is already about as big as the depth, right? And we know that when we have very high levels of H over D, when those are greater than or comparable to 1, then we have a situation where foreshore effects are going to become important and the wave becomes what we call depth limited, okay? So our very back of the envelope depth limited calculation, we can do better than this, and we will in this example, but we would simply say that the largest wave that we're going to see at this structure is going to be in the deep water, and that's going to be about 0.6 times the depth, which gives us a wave height at the toe of the structure of like 4 meters. These are just ballpark estimates, okay? Number 2, run-up. One quick estimate for run-up for a permeable structure is twice the wave height, and we'll come back to this later. It comes out of the run-up graph versus the surf similarity parameter. That's basically the plateau, R over H of 2. So 2 times 4 gives us 8 meters, so we think, wow, we might actually need as much as 8 meters of freeboard. That's a giant structure, right? 8 meters is something like that. So that's number 2. Number 3 is transmission. We know transmission is based on relative freeboard. If the relative freeboard is 8 meters, which we require for the run-up, and the wave height is 4, that gives us a value of 2. That is a very high relative freeboard, and we would expect very low values of the transmission coefficient and therefore the transmitted wave height, okay? So these are very quick and dirty estimates. The last one is a little hard to do quick and dirty. You kind of need to use Hudson's equation, which is, essentially what we'll use for the detailed calculation. But if you plug in some reasonable values for Hudson's equation, you can see that we should maybe be getting an armor value somewhere around 1.4, okay? 1.4 meters. And I guess one thing I forgot to mention about the run-up is related to the overtopping. So if we don't want any overtopping or very little minimal overtopping, then we're going to set the freeboard equal to the run-up. And that's why I did a run-up estimate, but really what I'm doing there is estimating the freeboard that we would need and setting that equal to the run-up essentially. All right, very quickly, foreshore wave routing. We need to get this deep water wave to the toe of the structure because all of our design formulas want the wave height at the toe, okay? So the first way to do that is the foreshore routing. In order to do the foreshore routing, we're going to take the depth for the two different water levels. We're going to calculate the deep water wavelength. We're going to calculate the deep water wave steepness, and then we're going to go to the foreshore graph that's closest to that steepness. And fortunately, we have a steepness of 0.02, which is one of the graphs that we have for the foreshore routing method for the graphical method. Then for the x-axis of the graph, we're going to need to know the d, the depth. That's the depth for that particular case divided by the deep water wavelength, and you can see those values there. So here's the graph for a deep water steepness of 0.02. So you have to grab the right graph. I did that for you. We have a foreshore slope of, I believe it is 1/50. And if you look at the graph, you get these values. So 0.62 for the high water and 0.66 for the low water. Essentially, we end up being kind of here for one and then here for the other. Okay, so 0.62 and 0.66. So that's what we need to do. And that is the maximum significant wave height that we would expect. And that would occur if the waves are depth limited, basically so big that they're breaking to dissipate energy and they're going to get dialed down to this maximum. We have to compare with linear wave theory. Okay, so for linear wave theory, we're going to take those depths. We have our offshore wave over here. We're going to route it down our spreadsheet like you see here. Same old spreadsheet we've been using in the class for linear wave theory. We start out in very deep water. I just said 1,000 meters. You could say 100,000 meters if you want. It doesn't matter. That's deep for this period of wave. We start with the 6.3 meter wave height and we route it to whatever depth we're thinking about. In this case, this would be the shallow water case up here, and you get a wave height. In this case, we get 8.23, and I've written down these linear wave heights up here. And so now what we're going to do is we're going to take the smaller between the linear wave height and the foreshore routing, okay? And so you can see that in both cases, the foreshore wave height is smaller than the linear wave theory, and therefore we're going to use the foreshore routed wave height. Okay, so that means also that the waves are breaking, and it's important to note that they're breaking because the armor stability formula, the Hudson's coefficients, want to know whether it's breaking or not. There's a different value depending on whether the wave is breaking or not. Just to remind you, linear wave theory, a trip down memory lane. I know you're getting very, very familiar and comfortable with the foreshore wave routing at this point, and that's great. We still need to be able to compare against linear wave theory, and so you might ask yourself, you know, in a scenario where you only knew the wavelength, the dispersion relation really just comes into this point right here. Could you actually calculate this wave height over here? And I think the answer is, with a little bit of jogging of your memory, you probably could. Okay, so the equation that goes into the wave height is nothing too bad. The cosine terms go away because for the foreshore routing method, we can only do perpendicular waves, at least as we've learned it. So all you have to do is this part of the formula, and you can check that on your own, but that's what you would get there. This wavelength here is the L2, okay? So just to remind you how we get the linear wave heights, okay? But in this case, both of the linear wave heights are bigger than the foreshore wave heights for both of the depths, and therefore we're going to go with the foreshore depths, or sorry, foreshore wave heights. So in summary, what I just said. Additionally, from here on out, you know, we have these low water and high water cases. There's a couple things we're interested in here from a design standpoint. One is armor stability. The armor stability is going to be most critical with the largest waves, and the largest waves in this case are for the highest water, so that would mean we would focus on that case for armor stability. Run-up elevation is always going to be greatest for the biggest waves and also the highest water level that you're starting from, okay? So both of those go with the highest water level for run-up as well. And the same is true for transmission, a bigger incident wave height, which we have for the higher water levels, and a higher water level, meaning lower freeboard, will result in more overtopping and potentially more wave transmission. So all of this suggests that the only case that we need to look at for this emerged breakwater, not the case for submerged, but this is the case for the emerged breakwater, is the high water case, okay? This example was helpful, though, in reminding us of one important thing about deep water versus shallow water in terms of wave breaking and foreshore effects. Shallow water is very effective at filtering out wave energy, right? And we see that here. The wave height is only 3 meters for the low water, whereas it's 4 meters for the high water, even for the same deep water wave offshore, okay? So one key idea is always that shallow water will filter out wave energy and you'll have a lower wave height. All right, but we're going to focus on the deep water case. One other thing is you may want to use the GOTA equations for your foreshore routing. And if you do so, you'll notice some differences between the graphical method, which is the 4.2 and 3, and the GOTA method. And one of the reasons is that the GOTA method gives you the significant wave height, which in deep water is equal to the spectral significant wave height, but in shallow water they can start to differ. Okay, so that's one of the reasons why you wouldn't necessarily expect these two to be different. Why would you use one or the other? It depends on the formula that you're using and what that particular formula wants. I'm not going to be too picky about what we're going to be plugging in. We're just going to use these foreshore wave heights over here for the design. But in actuality, certain formulas want the significant wave height and certain formulas want the spectral significant wave height, which makes things kind of complicated and gets us into the weeds, and I'm trying to highlight the big picture stuff here. So something to keep in the back of your head. One other thing to remember is that we are neglecting refraction, and refraction, at least when the bathymetric contours are straight and parallel, would diminish the waves. So we're kind of looking at the worst case scenario for these offshore waves. If they were hitting the structure at an angle, most of the things that we're calculating, if not all, would be reduced. Okay, first one is overtopping. So we are going to use this criteria that we'll talk about later in the lecture, where we're going to say, okay, if we don't want overtopping, we're going to set the freeboard, R sub C, equal to the run-up, RU 2%. They're not necessarily equal, but for a design calculation, we're going to set them equal, and then we would expect to have very minimal overtopping. Our wave at the toe is the deep water case. We have the deep water depth here, the 6.8 meters, and the 4.2 meter wave height. And now we just need to calculate the run-up. Hopefully this is kind of familiar to you. We go to Eurotop Chapter 6. Chapter 5 is for smooth structures. Chapter 6 is for rough structures. Notice that the title here, Rubble, Slopes, and Mounds, Armored Rubble, Slopes, and Mounds. So we just apply the formula, the different variables. We should expect to be somewhere along this data here. We have a permeable structure, so we should be along that line that I just sketched there. This graph does not account for any angled reduction or any berm reduction, which would knock things down from where the data are here. Anyway, we can just go into the formulas. We need our surf similarity parameter. This is a weird one where we grab the wave height at the structure toe, and then we grab the wavelength in deep water, so over here, and it's not the regular wavelength, it's the M-1 wavelength for that period, the spectral period. Not too bad. We typically assume that this period is the peak period divided by 1.1, which isn't always valid. It's valid in deep water, but it's what we're going to use. We're just going to use that as sort of a placeholder to note that we do need to convert between the peak period and the spectral period. Anyway, if we do the calculations, we get the structure slope for our slope is 1 over 1.5. The wave height is 4.2. Deep water wavelength for the spectral period is 253 meters. We get a surf similarity parameter of 5.2. Now we go to the formulas or the graph. In terms of formulas, Eurotop always gives you two different options. One is the mean value approach and one is design and assessment. Design and assessment is when you're doing design and assessment. It's more conservative. It will lead to a larger value of run-up. If you are designing, you want to be on the conservative side. Better to overestimate than underestimate for something like run-up in the freeboard. So we need our reduction factor. We have a gamma sub f of 0.4 for 2 layers permeable core. And we just go through the formula box and calculate these different lines. The first line gives us a non-dimensional run-up of 3.6. Then we get 2.3. in order to get that second line, we needed to calculate this gamma F subsurging. You should try these out on your own to make sure. We choose the smallest of these two and this one, which means that this 2.14 is our answer. And that's why initially our ballpark estimate for run-up was 2 times the wave height. Actually 2.14 it turns out, but this is sort of the upper bound for what you would expect for run-up. So our run-up ends up being 9 meters, close to the 8 meters that we surmised, and that is a very, very large structure. Look at the water depth here, it's 7 meters. Now we have an additional 9 meters up here. All right, moving on. Double check with the graph. It makes sense. 5.2, we're on the data. We don't expect to be below the data because we don't have any additional reductions, and therefore this is a good check. So those formulas, taking the minimum, basically ensures that you, ensures that you track along this, this set of curves. All right, we get the crazy, I feel like that looks like a Cubs guy. I don't know why. Cubs colors. Anyway, wave transmission. Here we go. Required transmission coefficient is set by the wave height that we want on the other side. That's over here, 0.6 meters, divided by the incident wave height at the toe, 4.2. We need a pretty low transmission coefficient. Fortunately, we're going to see that we can do that. Okay, so here's our graph. This is a simplified graph. If you're using this graph, you better be sure that you have a very standard shaped breakwater, nothing funky. And then you're also going to follow up with more detailed transmission estimates from this graph. This is good for sort of getting us started with design. Anyway, that was a big caveat to say don't sue me if your breakwater transmits more than you get from this graph. Required freeboard, okay, so we have an RC over H, so that is our in order to have the transmission coefficient of, we do it kind of in this direction. We know we need this transmission coefficient, and now we work our way down here and we get a value of about 1.1. That's for the relative freeboard. We know the wave height at the toe, and we multiply through by that, and we get a required freeboard for the wave transmission of 4.6 meters. All that to say that if all we care about is the wave transmission, knocking that down to 0.6 meters of wave height on the harbor side, we only need 4.6 meters of freeboard, okay? And that really is a lot less than the 8 meters of freeboard or 9 meters of freeboard that we need to have no overtopping, and we'll come back to that later, okay? So it's not actually that hard to knock down the transmission with an emerged breakwater, okay? Last one is the rock armor sizing. How big do these little nuggets down here need to be, okay? So for that, we go to Hudson's equation. That's our go-to. Hudson's equation, so for any sort of stability, it's typically this, where you have the actual stability parameter versus a critical stability number for that particular situation. Hudson's equation gives you the critical stability number as you see there, okay? So that KD cotangent of alpha to the 1/3. There's a lot that goes into the KD value now that really places a premium on choosing a good value for KD, okay? And so if we go to Hudson's experiments, we can look up a value that's reasonable for that. This is the formula that you get if you multiply by the specific weight of the stone to get the weight of one stone. If we're following the shore protection manual from '84, we actually need the 1/10 wave height. That leads to a pretty conservative estimate in terms of the armor sizing, but we typically do that in this class. A deep water conversion between those two, the significant wave height and the 1/10 is 1.27 times HS. We're not in deep water, but we're kind of putting this here as a placeholder to note that we need to be plugging in this 1/10 wave height into Hudson's equation, at least according to the prescription laid out by the Shore Protection Manual in '84. Anyway, here are some KD values, and now all we need to do is figure out which one is for our particular case. I believe I said we had special placement, or if I didn't, I meant to say that. We have rough angular, we have breaking waves because we're on the foreshore curves, and so we're going to use a value of 5.8, okay? Notice that non-breaking has different values and breaking has different values. And that's why knowing whether or not the wave is breaking is important, because if it's not breaking, you can get by with smaller armor. Notice KD is in the denominator there. The bigger the KD, the more stable the situation is, and the lower the size of the armor that you'll get, okay? So it's not a huge reduction. You know, we're going from 6 to 7, but it is an important enough one that we can make. All right, I'm out of breath, but if you plug in the numbers, you will get 113,000 newtons, and I don't know that anybody ever specs out rock armor in terms of newtons, so some other units, 11.5 metric tons, or one we can all appreciate, a DN50 of 1.6 meters, okay? So 1.6 meters, 160 centimeters, maybe, chest high, something like that. But these are pretty big rocks, okay? And this is a pretty big wave that's hitting this particular breakwater, okay? If you want to know what numbers I plugged in to get those to work, they're over here. And there you have it. One other thing, we could estimate how much armor we need. So if we are not doing any overtopping at all, we probably don't need armor on the backside of the breakwater, okay? So I just kind of covered that up. And this is just a quick and dirty estimate of how much armor we need. How would we do this? Well, it turns out that the DN50 is a good estimate of the amount of space that a single rock takes up when it's aligned with other rocks. What I mean by that is that if you had 3 rocks kind of stacked carefully next to each other, it would be roughly 3 DN50 long, and etc. Right? If you have 10 rocks, it's 10 DN50. So even though none of these rocks is equal to the DN50 in terms of its dimensions, DN50 is the equivalent cube length, it turns out that by and large, it's a good dimension to use for thinking about how rocks pack with one another. All right, so how do we figure out how many rocks we need? Well, we just do a bit of geometry. Our breakwater needs to be 15.8 meters tall. I got that because it's 6.8 meter depth plus the 9 meter of freeboard, 15.8. We know the angle here, 1 to 1.5. And this dimension by trigonometry is therefore 28.5 meters. If we divide through by the DN50, we get that we need about 18 stones to fill that diagonal there. Now we don't just have one layer, we have 2 layers, okay? And we don't just have armor there, we also have it on the crest. So this is the world's most quick and dirty estimate. Sorry for these other things getting in the way, but we have 18 stones, that's these guys down here. We multiply by 2, we get 36, that's for the slope section. We get 3 times 2 for the crest. The crest is typically 3 stones wide. We add all that together, we get 42 stones, and that is 42 stones just kind of for one page, or just, what you see here. And that goes into the page by 1 stone, which is 1.6 meters. So that's 42 stones per 1.6 meter into the page, which is 26 stones per meter of breakwater into the page. So if that breakwater was 100 meters into the page, we would therefore have, 2,600 stones total, armor stones. And then you can do things where you figure out, like how much does all this weigh? We know the weight of each stone from before. And basically we get 300 metric tons per meter into the page. And so that would allow you to figure out what is the total weight of armor that you need for this breakwater if you know its length into the page. And that's useful because if you know how much it costs, then you can kind of start costing out, some of these different options or geometries. Anyway, just threw that in there for kicks. So in summary, this is what we need. We routed our wave to the toe. We focused on the deep water case because everything was going to be worse for the deep water case. Bigger waves, bigger water levels, more run up. We calculated the required freeboard for overtopping, which was immense, 9 meters. That's like the Taj Mahal of breakwaters. We calculated the freeboard needed for transmission. That's quite a bit less, 4.6 meters. We calculated the size of the rock armor for the worst waves that we think are going to hit this structure, at least the design wave, 1.6 meters for the DN50, 11.5 metric tons per boulder, okay? So just a couple of thoughts. Oh, first of all, how did that compare to our estimates? Very well, okay? So Hudson's equation, we're kind of comparing Hudson's equation with Hudson's equation, so that one's kind of cheating. But the wave at the toe ended up being pretty close to what we estimated. The freeboard was a good estimate, that 2 times the wave height is an extreme. And then this idea that 8 meters is more than certainly good enough for knocking the transmitted wave height down to 0.6 was certainly true. We only needed 4.6 meters of freeboard. So these are our sanity checks, and all these values kind of make sense, okay? What doesn't really make so much sense, though, is this 9 meters. I've never heard of a breakwater that tall, at least in terms of the freeboard, right? That's 9 meters above the water level, right? And so let's think about this a little bit more. How could we make this breakwater smaller? A couple of different ideas. One is you could build a berm over here, so you could build a berm that would help to reduce the wave height and therefore the run-up. That would be a berm reduction factor that you could actually calculate out and account for. What else could we do? We could build a submerged breakwater in advance of the regular breakwater that would reduce the wave height hitting the toe and therefore the run-up. Other things you could do is maybe you could make the breakwater lower but wider. So if it was, wide like this, then maybe overtopping wouldn't be such an issue, and you would be allowed to do more with overtopping. Okay. Just comparing this breakwater that we just designed to other breakwaters. This one is the 31st Street breakwater. Notice that we have 4 meters of freeboard from the highest water, so much lower than our 9 meters of freeboard. If you look at the Long Beach breakwater that we looked at, this is very deep water, right? This is 50 feet deep. Those are big ships that are going in and out of this harbor, but still only 4 meters of freeboard, okay? And again, we calculated 9 meters of freeboard, which is way up there. So what's going on with our calculation? So it goes back to our design constraint where we said we want no overtopping, okay? So that, it turns out that's a very extreme constraint that's not so appropriate to rubble mound armored breakwaters. The original intent of the 2% run-up is basically that if you set your crest elevation, like we did for our structure, if you set the freeboard equal to the 2% run-up, then you will have minimal overtopping, and it was originally intended to be used for dikes. So a dike is, no water on one side and water on the other side, and it's essentially protecting low-lying areas from the ocean. And the Dutch found that if you set this constraint, the freeboard equal to the RU 2%, you would not need to worry about any sort of scouring on the backside, because these structures are not armored and they really can't have any scouring, or else the whole thing will start to fail. Okay, so this is for an unarmored structure, this idea where we set the run-up equal to the freeboard. This would be appropriate for this kind of structure that you see down here, but for an armored structure we can actually tolerate some overtopping, and we can actually tolerate sometimes a fair amount of overtopping if we engineer it to do that, okay? And so Eurotop is essentially an entire design manual that is looking at this issue. How much overtopping is okay? First of all, how do we calculate overtopping? And second of all, how much overtopping is okay for a given kind of a structure, okay? And if you look at Eurotop, you'll see all sorts of different metrics that people use to quantify the amount of overtopping. Sometimes they use an overtopping discharge. Sometimes they talk about the volume of water plopped on the other side from a given wave. Both of those, it turns out, are important in terms of assessing the amount of overtopping and what is tolerable. But it's essentially an entire design manual answering this question: how big does the freeboard need to be in order to have a certain amount of overtopping? Okay, and because it's big dollars, right? If you can knock the breakwater height down, the freeboard down from 9 meters to 4 meters, that's a huge savings in cost, right? And also aesthetics, right? Nobody wants to be sitting in their boat staring at this concrete monolith in the middle of what should be, a beautiful ocean kind of a setting, okay? Anyway, that was a lot to talk about, whether the answers make sense, but I wanted you to think about that. The numbers that we got were good for the constraints that we assigned. It's just that the design constraint of no overtopping for a structure like this that can clearly withstand overtopping is kind of extreme. And if you look back to the 31st Street breakwater, you'll actually notice this is the wave side over here. So one of the key design flaws here for this breakwater is that the waves actually, they designed them to come from right to left, and as you know, waves come from left to right. Anyway, some wave humor there. But I digress. Notice that there is armor all on the wave side, all on the crest, but actually all the way down 2/3 of the backside. So this structure, because it's armored on the backside pretty heavily, can withstand a significant amount of overtopping, and undoubtedly that was factored into the design that you see here, was, making sure that the armor and the placement was okay for the design wave and the amount of overtopping that wave would cause, okay? So that's how you're able to do much less freeboard than what you would calculate for no overtopping. Anyway, I digressed and then I regressed, and now I think I'm ready to sign off. So hopefully that was helpful. The intent was to kind of show you how all the different pieces come together for the things that we learned in this class. Have a great evening, morning, afternoon, midday, wherever you're at.